Thank you again to the organizers. As everyone has said, it's absolutely required to thank them for running such a great show here, and especially to Ray and Philippa for dealing with all of my registration issues in particular. My voice is a bit weak today, so I'm sorry. I've had a bad cough for a couple of weeks. Hopefully it'll hold out. So this is some work I've been doing with Tony Del Genio for the last few years. And I hope it'll convince you to think a bit more about Venus as an exoplanet in a sense, because there might be some stuff that we're missing out there. And I hope I can convince you that this is a possible scenario anyway, amongst many others. So what is the motivation in some sense for Venus as an exoplanet? I don't think we should rely only upon Earth through time as our only indicator of habitability. That's what we really basically rely on today for most of our modeling. Of course, Paleo-Mars and Paleo-Venus may offer some useful habitats. And hey, maybe Venus is simply interesting. I mean, this is probably the first conference I've been to in a long time that wasn't a Venus conference where Venus was mentioned more than Mars. So I give you people a lot of kudos for that. That's because it has interesting stuff in its atmosphere that Mars doesn't have. Okay, so thankfully, and I knew this before and that Laura was going to talk about magma oceans, so that makes my life a lot easier. But I think we have two basically scenarios here for how Venus could evolve through time. Both Earth and Venus probably start out, as Laura was talking about, in a magma ocean phase. And after a few million years, Earth would have cooled down and had some sort of atmosphere. As we know, CO2 dominated and N2 dominated. The question is, what could have happened to Venus? Could it ended up in a scenario where it also cooled down fairly rapidly after the magma ocean phase? Or has it always been this very dense CO2 dominated N2 450 degree centigrade beast for its entire evolutionary history? As I said, that longevity of the magma ocean is crucial, as Laura showed out. There have been some very nice work by Keiko Hamano that Laura showed that basically shows that if the planet's magma ocean stays around a bit too long, say order 100 million years, you outgas all of your volatiles, and this planet is bone dry from the start. And that work has been backed up by others since then. If you look carefully at the Hamano paper, though, Venus sits right at the margins of where they believe that it will either go one way or the other, be type 1 or type 2. So we actually don't know. And we probably will never know until you people get us some exoplanet data on really young Venuses around G-dwarf stars, right in the right phase. And we can make some observations, find out. If we see a Venus that's only 200 million years, or say 50 million years old and has no magma ocean, that could be very interesting for understanding the evolution of these magma oceans, and in particular, our own nearby neighbor. So the question is, was all the water lost? And is it possible to get some water back through the late Veneer? Because we know that, of course, Earth, its magma ocean didn't stay around too long, and there has been some work by Greenwood and others from 2018 that says the late Veneer could have added between 5 and 30% of Earth's entire water budget. Now, they're pushing the envelope, of course, on those kind of numbers, but imagine if you could get the same kind of water delivery into Venus later on. Even if it lost its magma ocean, as long as the surface is relatively cool and the atmosphere is not crazy hot, it might get a second chance, actually, at being a kind of a thin veneer of water and having some kind of reasonable evolutionary history comparable to that of Earth. Okay, so then the question becomes, is there really any evidence for surface liquid water in Venus's history? And if so, then clouds in concert with rotation rate may have played a key role in Venus's climate evolution. Some of that is work that you will have seen before. So did Venus have surface liquid water? We believe for most of the planet formation models that they probably started out with around the same amount of water as Earth, given their similar masses and given their proximity and the original disk of our solar system. I mentioned this late Veneer business that would have also added some water. The key measurement that we have for Venus is really this high D to H ratio that's about 150 times time terrestrial we got from the Pioneer Venus mission way back in the 1970s. The whole problem is that we don't know the time scale of this water loss. We don't know if this was the original water with that original steam atmosphere from the magma ocean days, or was this water lost very rapidly in the last 100 million years, or was it lost very slowly over several billion years? That's information we can get, but which we do not have today. There have been some other observations from Galileo NIMS. This is a paper from Hashimoto in 2018, who came up with the idea that a lot of the highlands appear to be composed of felsic rocks, and that could give us some indications that there's some granitic material there. If you have granitic material, you have water at some point in its history. Whether everybody believes in this or not, that's up for debate. But it's an interesting idea. Then there's also this very interesting 2 papers from 1990, and then the work was done in 2019 as well by Shellnut, that through some quite modeling-dependent aspects, believe that Veneer 8 probe might have encountered a fragment of a crust from the original Venus that resembled a terrestrial greenstone belt. Again, very modeling-dependent, but very enticing. But that's all we have, basically. That's the only evidence that we have that there might have been water on the surface of Venus at some point. It's not very much, I admit. It means that we're a data star field, is what it's telling you. Okay, if we assume that we have some water on the surface, then we go back to some really great work by Jun Young and some other people in this room that show there's this very strong dependence on the inner edge of the habitable zone on planetary rotation rate. So these are 2 figures that people are using all the time now. And on the x-axis here on the left, you see the incident stellar flux on the world. And you can see in early Venus from about 4 giga-years ago, that's the kind of flux it would have had, and even modern day Venus. And then each one of these curves is a rotation rate speed. So 1 is Earth's rotation rate today. 16 is 16 times Earth's sidereal rotation rate, 64, 128, and 256. And the key result from this paper, of course, is that there's this kind of dichotomy between slow rotators and fast rotators. So as you amp up your solar insolation on these worlds, these fast rotators quickly go into a moist or runaway greenhouse state, whereas the slow rotators, they heat up much, much more slowly. On the right, you see the very similar figure for the same colors, for the same rotation rates. And what you see here is planetary albedo. And the key thing here is you see the planetary albedo is rocketing up on these slow rotators. As I think most of you may know who know something about these papers, that's basically because the planet is slowing down, of course. The Hadley cells are increasing in size, and you're getting a large cloud convective front at the substellar point, a very massive sort of anvil cloud at the substellar point. And that's shown in this very nice figure from Jun Young. On the left, we have a rapid rotator. This is the percentage of clouds, and you can see the cloud is a very banded structure. And on the right, you can see for the same solar insolation, a slow rotator, 128 sidereal day, where we have this massive cloud, convective cloud at the substellar point. And this is what drives that very high planetary albedo, and that's what keeps the surface warm, and that's what allows these slow rotators to move the inner edge of the habitable zone in quite far. Okay, now I need to ask you, like, what do we know about Venus's rotation and obliquity? Because I've just explained to you that if Venus has had water, it has to have the right rotation rate for it to have the climate that's possible for having some sort of habitable conditions. So the question is, has the rotation rate evolved through time, and what are the prevailing theories today? So there's a long history of looking at this stuff. I think the most popular hypothesis is a paper that actually isn't even a paper. It's just a conference abstract, but everybody cites it like it's the greatest thing. And you read popular science articles, or you read even quite reasonable publications who say Venus has the rotation rate and obliquity it has today because of a massive impactor. But nobody's actually done the dirty work on this, if you can believe it. No one's done a simulation, anything like the work that Robin Knoop has done for our own planet and moon. It's never been done. Nobody's interested. So it's low-hanging fruit for some ambitious graduate student in this room, okay? So, we don't know. Then some earlier work from the 60s and 70s, looking at core mantle friction and atmospheric tidal torques, have shown that it's possible for the Venus to evolve in time, and also that involves some flips of the obliquity axis, basically, to drive it into the state it has. And that really goes back to this, like I said, these papers from Gold and Soder, Goldreich and Peel, Dobrovolskas and Ingersoll did the really first heavy lifting, and then Lasker and Correa basically have done this in finite detail since 2001 and forward. One thing that I found really useful and interesting was this great paper by Jeremy Lecomte and collaborators from 2015 that showed that all of these works here are assuming that you have this 90 bar atmosphere, and that is causing the tidal torque that keeps it in the retrograde rotation state. Basically, the idea before was that if you didn't have this super thick atmosphere, the planet would eventually end up in a tidally locked state. But Jeremy showed through some very nice simulations that even with a 1 bar atmosphere, you can still end up in a retrograde rotation state, which is really interesting for us. Okay, so in the meantime, we've done a couple more simulations looking at solid body tidal dissipation and possible ocean tidal dissipation, which I think you might find interesting. So these are some calculations that I've done using an equilibrium tide model developed by Rory Barnes at University of Washington. On the left is a constant phase lag version of that model and constant time lag version. I'm going to focus on the constant phase lag because it gives me the answers I want. We don't know which one of these models is correct, to be honest. I use a Q and a love number 2 that are values similar to modern day Earth for lack of having any reasonable Q values for ancient Venus. And we have not really great constraints on either of these numbers for modern Venus either. We're just a data star field. But the key on the left here is this constant phase lag model is that if Venus starts out with a 3-day rotation period in this model and ends up synchronous, 3 Earth day rotation, ends up synchronous in 684 million years. If it starts out with a 15-day rotation period, it goes synchronous in 132 million years. So the solid body tides on Venus will slow this planet down fairly rapidly, depending on what its initial rotation rate was. Just as context, this is a nice paper from Rory Barnes in 2018 where he uses the same model. He assumes that if Earth had not been hit by the moon and had started out with a 3-day rotation period, it would have gone synchronous about now. So if we hadn't had the moon impact, Earth would be approaching a tidal lock state as we speak, which would be kind of interesting. Because we always have this idea when we do our modeling of exoplanets that all these planets have the same spin state as Earth, right? When they're out at Earth orbit. That may not be a very good assumption. Okay, and this is another paper that I've been working on with Matthias Green at the School of Ocean Sciences in Bangor, Wales, and Rory Barnes. A bit more speculative, but the idea here is to use a numerical ocean tide model that is very commonly used in the ocean sciences community. We took a modern Venus topography with 2 different kinds of depth ocean. We did a whole suite of simulations using rotational periods from what Venus is today, -23, to prograde +64, sidereal day. And the tidal dissipation just from the ocean varies by 5 orders of magnitude, depending on where you are in this parameter space. And the maximum slowdown for this model is that it will slow down by 72 days per million years. So tidal dissipation from a shallow ocean on Venus is extremely efficient at slowing down the rotation rate of this world. Another thing we should be thinking about when we think about rotation rates of exoplanets. Should this be surprising? I'm not so sure, because on Earth, we already know that the tidal love for the subtle Earth is much lower than the tidal love for the ocean. So we already know that the oceans are much more dissipative on Earth than the solid body torques are. So that shouldn't be too surprising, although some of my friends who work in dynamics were surprised by this result, believe it or not. Okay, so now that I've given you all that, and I'm going to make these assumptions that the planet has been spinning slowly for most of its history, and that it had some kind of atmosphere early on, I'm just going to show you some fairly simple simulations. So this is using our Rocky 3D general circulation model. And I'm just going to talk quickly about a couple different atmospheres we tried. So we went back to 4.2 gigayears ago when the insolation that Venus was receiving was about 40% what Earth receives today. And I gave it a 100% CO2 atmosphere. Because there are some models that show that early Earth's atmosphere could have been very early Earth's atmosphere could have been a pure CO2 atmosphere before the nitrogen started getting out and mixing things up. And then we have another simulation, a set of simulations at 0.7 gigayears ago, where we're receiving about 70% more rate incidence flux than Earth is receiving. And we use a very modern Earth composition in that sense, assuming that some kind of carbon and silicate cycle would have taken place in the planet, carbon would have been drawn down, nitrogen would have gone up, and other species would have been produced. And then, given the fact that Venus's topography from 4 billion years ago or 1 billion years ago is completely unknown, because the surface of Venus is one of the youngest surfaces in the solar system. It's less than 1 billion years old. We know that from crater counts. We tried a whole slew of different topographies. So the first one we did the first 3 are using modern Venus topography in lieu of using anything else, because it's sort of the least worst choice that we have. The first one is an Abbe-type dune world, where we only put 20 centimeters of water in the soil. So that limits the amount of H2O into the atmosphere. And basically, H2O is an efficient greenhouse gas, as Laura showed us in some of her stuff earlier. Then we have another simulation where we put 10-meter water equivalent layer in lakes in the lowest lying regions of the planet. We let the planet evolve in time, and we let the model decide where the water should actually go. So it will do a calculation based on evaporation versus precipitation versus runoff, and it distributes the model quite differently than what you would expect from your initial conditions. And the third one was a 310-meter deep ocean, basically that we used in our 2016 paper, again using modern Venus topography. And then because everyone uses modern Earth topography, we also did that for fun. Of course, it never had modern Earth topography, but we just use it for a different kind of topography with a 310-meter deep bathtub ocean. We use these kind of depths of the ocean because the D to H ratio estimate does give us a very broad window to drive a truck through. From the Donahue and Russell papers from the 80s, they basically said that Venus could have had anywhere between 5 and 550 meters of water equivalently across the surface. So that's why we have a lot of room to play with here. And because aquaplanets are very popular in this community, we also did an aquaplanet just for fun. So instead of showing you lots of plots with lots of lines and lots of points, I've been inspired by Colin Goldblatt's talk back in CCTP3. So you can crucify him if you don't like my cartoon drawing of what I'm about to show you. So this is all of the simulations in a really fancy cartoon, I would call it, in a sense. So what you see on the left here is the temperature of the world, and then on the bottom axis you see a timeline from 4 gigayears ago where the insolation was 40% more than present-day Earth, 70%, and even I did some simulations today. What happens here is still completely unknown and unconstrained. As Laura said, we don't know how fast this planet cooled down. We don't know the time scale. We don't know what the atmosphere was even made of. But I'm going to assume, because of the ideas of using comparative climatology, that it probably had a CO2-dominated atmosphere. And if you take all those topographies I used for CO2-dominated atmospheres, the temperature ranges for any of those topographies, even at a CO2-dominated atmosphere, because of the slow rotation of the world and the effects the clouds have on the planetary albedo, I get a range of temperatures from somewhere around 30 to 50 degrees centigrade. So it's not a crazy world. The stratosphere in some of these models does have a lot of water vapor in it, which means the planet's going to lose what ocean it has over some time scale, which we haven't calculated. And then the idea, again, as I said, is that there would be some kind of carbon and silicate cycle. Of course, it won't be linear like this. It'll go up and down, and all kinds of things will happen. But the last simulation, or one of the last simulations we did, was at 0.7 or 0.7 gigayears ago, again with that N2 CO2 dominated atmosphere. And you get temperatures that are quite a bit lower. They're basically between 15 and 30 degrees centigrade, no matter what your topography is. Now, why did I kind of stop there? Because the surface is completely new to us. We don't know what happened, but the idea in this model would be that the planet evolved in time, and that what drove the planet into its present-day state was some kind of major overturning event, the results of which we see on the surface today, that very new surface we see on Venus. And that's what drove the planet into its present state, where the CO2 was released from the carbonates that were locked up on the surface into the atmosphere over fairly short timescales, say hundreds of millions of years. It will not be a catastrophic resurfacing. I think that's pretty much agreed in the Venus community now. It's not like this overturn event and the resurfacing happened like in a blink of an eye, geologically, which is 50, 100 million years. We're talking about hundreds of millions of years. But that will drive the planet into the current runaway greenhouse state. But we did do one more set of simulations, again, where we kept this sort of modern-day Earth N2-dominated atmosphere. And even today, at 1.9 times what Earth receives today in terms of solar insolation, the temperature of the atmosphere for any of these simulations didn't change very much. And that corresponds actually to a couple of simulations that Jun Yang actually did in his 2014 paper that don't get a lot of press. So I think this fits kind of nicely in with an old paper that I really like from John Valley from 2002. The paper's titled A Cool Early Earth. Now, John plots his axis the other way. So again, I took liberty and redrew his plot for you. So on the left axis, you see impact rate. There's some kind of planetary accretion here. And the planets, he does a very nice job of looking at zircon ages. He's gone all the way back to 4.3 gigayears ago now in his 2014 paper to show that Earth probably had this cool period very early on in its history. Back then, there were a lot more proponents, I would say, in the community for the LHB, but I think that a lot of that, that enthusiasm has gone by the wayside in recent years. But if this is true, these zircon measurements by Valley and many others, we probably certainly had low surface temperatures. We had liquid water. We have continental crust. That's work that's also been supported by a couple of really nice papers by Korinaga and collaborators. And just yesterday, I saw this paper by Mojis and Brasser, who are at Colorado, and LCN collaborators that show basically the same thing. They have some very beautiful plots in their paper that show almost the same thing as Valley has here, but without the LHB, because they are not proponents of the LHB, the light heavy bombardment. So this kind of fits nicely into that picture I showed you for Venus. If the planet can cool down early, then you end up in this very cool early phase pretty easily. Again, depending on rotation rate for Venus and that it has surface liquid water. For Earth, we don't have that problem. But in the interest of comparative climatology, I thought this was a really interesting picture to see. Okay, so I would also like to talk about this in the sense of the Kane zone. I'm sorry, I meant that the Venus zone. That's a reminder for you guys to all go look at Stephen Kane's poster tomorrow on Venus as an exoplanetary laboratory. So our idea here is that we have this Venus zone, which people basically have been ignoring for years in terms of the habitable zone. And I want to promote the idea of what I call the optimistic Venus zone. We always pick these ridiculous labels for things: optimistic habitable zone, pessimistic habitable zone, conservative habitable zone. Pretty soon we're going to have like the Trump habitable zone. But I want to stick with the optimistic Venus zone is what I want to promote to you. And that we shouldn't discount all of these worlds sitting in here. We have to know the rotation rates of these planets before we really go looking at them. And maybe we're 10 to 20 years away from doing that. Depends on who you talk to and what they think our next generation of telescopes are going to be capable of. But we shouldn't discard all these, just like we shouldn't discard our nearest neighbor, which is completely neglected by the planetary science community for the most part. I mean, Mars gets a mission every 18 months or more, and Venus gets a mission maybe every 10 years if it's lucky. We haven't had an in situ mission to Venus since the 1980s, basically. That's why we don't know anything about this planet. And one other thing I want to show you very quickly that our model outputs at the very end is some direct imaging spectrum. Now, there's no noise model in this or anything. But on the left, you can see that CO2 dominated atmosphere is very easy to detect. You have these very large bands, CO2 bands, that would be very easy to detect compared to the N2 dominated atmosphere in terms of the thermal light that you can detect from them. This is from 4 to 20 microns. So this kind of thing would be observable even in a fairly young Venus, even a few 100 million years old, if it had these kind of surface habitable water conditions. Okay, so I want to try to keep my talk short. So my point is that if a cool early Venus had surface liquid water, it's not clear that solar luminosity is the defining factor in its climate evolution. Why do I say that? Because I read things in the popular press about this all the time. Venus had liquid oceans, and as the sun got warmer and warmer, the oceans boiled off, and it was the end of the world. Our models do not show that in any way at all. And this guy is one of the guys to blame for it. Paul Sutter at Ohio State. Here it is. But as the sun aged, that habitable zone steadily moved outward, and as Venus approached the inner edge of the zone, things started to go haywire. This guy doesn't even work in this field. Okay, anyway. Optimistic Venus zone, exoplanet habitability estimates require rotation rate knowledge. I think I've convinced you. We need Venus in situ observations to confirm its geologic and volatile history. That means all these beautiful noble gases and all of their isotopes is the only way we're going to know if this planet ever had liquid water in its surface and when it lost that water and how it lost that water. No mapping mission, nothing from orbit's ever going to tell us any of that. So anybody ever tells you, I'm going to do an orbital mission for Venus, it's going to be so great, we're going to get all this, you can tell them, no. We need noble gas abundances. And so for this reason, I give the Russians great credit. They're really trying hard to redo the Vega missions, but kind of amped up once more, to do one more mission to the surface. Some of us are going to Moscow next month to do some landing site selection and hope that NASA will pony up some money to put a balloon instrument on this mission and get us these noble gas instruments in situ on the surface from that Russian spacecraft. The question is, will Venus's history constrain possible exoplanetary climates? Don't know. It depends if we go back to the surface of Venus, and otherwise, you're going to tell us everything about Venus because we ain't going to know shit. Our nearest neighbor is going to be sitting there waiting for us to make some. Anyway, thank you very much. I'm so glad my voice held out.
We have time for questions.
Edwin Kite, University of Chicago. What observation, either from noble gases or other sources, would disprove the early habitable Venus hypothesis?
What would disprove it? Well, if we find out that it lost all of its water in the first 100 million years, that the noble gases will tell us that. That's all we need.
Hi, that was an excellent talk. Thank you. A lot of the work that shows the dependence of the state of the sensitivity of the climate to the rotation rate will depend on cloud feedback parameters. So yes. Has any of the uncertainty of that, or maybe convection scale modeling, been looked at?
Not in detail, no. But it has been seen in 3 different GCMs that have coded up their cloud convection schemes in completely different ways. So that's all I can say on that. I was encouraged by, where is he? Where's his talk? I was encouraged by Dennis's talk. Sorry, by Dennis's talk yesterday that showed this very detailed cloud resolving model and its comparison to the GCM. I don't think he did it on purpose. It was kind of portrayed like the GCM doesn't do a very good job. But actually, I think the GCM did a very good job. If you look at his figures very carefully, it mimics very nicely what the cloud resolving model is actually doing. So I think the GCMs are doing a quite good job. We have also completely rewritten our cloud convection scheme for our next version of the model, the Earth climate model that's going to come out next year. And we're going to release a planetary version of that. And it's one of the first things we're going to test out is how different do they look, basically.
Down here.
Martin Turbet from Geneva Observatory. I would like to know if you explored whether this cloud feedback could also work if the background pressure was higher and if they were like a thick CO2 atmosphere. Is it something that could be robust to thicker atmosphere?
I think it is. I've only done a couple bars CO2. My goal is to do up to 10 bars because we have the radiation tables for that. And I just haven't gotten around to it. But I think it's a really great idea. I mean, I put a proposal in recently to one of the ROSES programs to work with Roxana Lupu, some of whose data Laura showed, and Mark Marley and Kevin Zonley, and Stephen Keynes on that proposal too, to really redo some of those Himano models and Lupu's models very early on, but put clouds in. Actually, they don't have clouds in those models. So we are going to put clouds in and then bring those models down from, say, 1,000 bar atmospheres, whatever you want, very high temperatures, and then down to where my model can meet them, say at 10, 30, 40 bars, because their models are all, much lower dimensioning models, obviously. And then see if we can tie up, assuming that their models are giving answers that are useful to our model's inputs, basically down the road. But yeah, we definitely want to do that.
Yeah, I mean, going back to one of Casting's early papers, he remarked that clouds would tend to inhibit the true runaway greenhouse for early Venus, but he argued that the moist greenhouse effect, or what I call the wet runaway, would lose the water just fine anyway. And so you mentioned that your stratospheres get moist in a lot of these cases, and so yep. I just wonder whether that just negates this whole habitability range.
Yeah, it's a good point, Ray. It depends on which simulation it is, and the stratospheres are not always the same wetness. And I haven't done the actual calculations to know, what the longevity of those oceans are. I mean, in Casting's paper, he loses a whole Earth's ocean, but over 4 billion years. So it's not like if the stratosphere is as wet as he says it is, it's going to lose it in a billion years or 500 million years. It depends on how much water vapor is up there and what is the incident flux on the atmosphere. So it depends. But you might like to know that Jim Pollack also wrote a paper in 1977, I think, where he does the same thing. He uses a 1D model. He uses 100% cloud cover for Venus, and he gets 300K for the surface temperature. He's the first person to ever do that. Actually, funny enough, he didn't know why he used 100% cloud cover, but it turned out it was a good choice for reasons he didn't understand.
Maybe one more question.
So I'm going to make it two, but the first one is quick. Do you think we should go back to the surface of Venus?
No.
Okay. The other is actually I got a little fixated on a small point you made about how if it weren't for the impact that forms the moon, the Earth might be tidally synchronized by now.
Yeah.
And so this may set our expectations for exoplanets.
Yes.
But then I'm also remembering that during Laura's talk, you referenced some paper that predicted that planets should in general have a few impacts during the planet formation process. And so I'm wondering...
2 or 3 was what her model showed, I think.
Right. And so if we think that most planets should have some impact, how does that plus this information set our expectation for rotation rates of terrestrial planets?
Good question.
Anyone?
Like I said, I would like someone to do the moon impact for Venus and tell me, can you get retrograde rotation rate out of that impact, depending on what the rotation rate of the world was to start? Those are really good questions. Yeah, we don't know.
Okay, and on that note, let's thank our speakers again.